Okay, so thank you for the invitation, for the presentation. And so today I'm gonna talk about these new like works that we've done past years about how can we say something about frustrated system starting from the analysis of the structure. And this is because our background basically comes from network, and we studied by during the university years like also the disordered systems, and at some point the two things coalesced and emerged into these works. So we start with the first part with introduction on the didactical, a bit of didactical and inspirational introduction of the few concepts that I will mention in the second one. And in particularly, the core is of concept that we need is the concept of conflict. How do we encode it? How do we represent it for system? How does frustration emerges when you represent conflict? And how this is linked to the spin glass theory? And finally, how diffusion can, in general, is used in discrete system to probe their structure and tell something about the properties of this coming from the structure itself. So we start with a very introductory and philosophical slide. So conflict dates back way before physics came, and it's like driving mechanism, as Gramsci remembers us, of the human history. But in general, nowadays we would say of any complex system, from ecological ones to social networks, and even in the brain, where the ratio of excitation inhibition 80-20 is like sits at the core of this perfect balance that allows intelligence to work and intelligent life to go on. So the minimal units to encode the conflict is like the negative -1. So if you can imagine to represent the conflict in the most minimal way as a two-node system with a link in between them, and you have a binary system, you can be in +-1 state, and you associate a cost function to your system. Then if your cost function is just the product of these three elements, you will discover that if the link is positive, the two nodes will like to stay in the same state, while if the link is negative, they will put themselves into different, into opposite states. And so this is the minimal coding of conflict, and up to now, we don't see any richness or any unsatisfiability coming out of this. The moment you add a third element to your system, keeping the same formalism for your cost function, what happens if you put a negative number, an odd number of negative signs on cycle in the couplings? What happens is that frustration emerges. That is, there is no more a state in which the system likes to settle. Rather, there are three states up to symmetry that the system can surf without changing the cost function. And so there is an intrinsic undecidability of the system state a priori based on the minimization of conflict. If you keep adding more and more elements to your system, you step into the so-called Edwards-Anderson model, which is the coupling of quench disorder, where now you draw your couplings from this probability distribution, and you encode your cost function in these two-body interaction. And basically, the phenomenology is really interesting, because if you compare to Ising magnet, what happens is that you don't have anymore two simple phase, the ferromagnetic and the paramagnetic phase, but a new phase, which is intriguing because is disorder at low temperature, emerges. And in particular, this emerges with an anomalous transition, and the landscape of the energy of your system becomes really rugged and dominated by exponentially long-lived states that don't allow you to find the minimum of your energy landscape in a simple way. That is, you find yourself in a MPR problem if you want to find the ground state of the system. So very shortly, the right order parameter in this case, you cannot use magnetization, otherwise you would mistake this for disorder. But if you compute the overlap between different realization and you then follow Parisi recipes of computing the distribution of this overlap between replicas of the system, what happens is that you observe a non-trivial structure, and this order parameter becomes an infinite number of order parameters due to the fact that you have this infinite number of minima landscape, where there is this sort of emerging ultrametricity property between the overlaps of replicas that is telling actually you that some structured order is coming out of your quenched disorder, your frustrated quenched disorder. So there are some open questions already here. So where does this euthymetric structure lives? Can it be detected without invoking the dynamics? Is that the structural property of the system before you start analyzing in this dynamics? And what is the real mechanism that drives this fragmentation of the energy landscape? And the last one, can we identify some, and it's related to the first two, is can we identify a structural parameter for identifying this glassy phase before we even mention the energy function? And also, this is our last point of the introduction. We are inspired into the next, in what follows from the diffusion process. That is one of the most basic processes in physics, and is the driver of many other ones, and is on top of which many dynamics are built. And we know that in continuous space is represented by the differential minus Laplace-Beltrami operator, which becomes in the graph language, when you discretize your space, you can recover the operation done by the Laplace-Beltrami operator if you simply consider your coupling matrix and then you subtract the degree matrix, which is just the sum over the rows. Then the diffusion process is really reads very easily as the time derivative of the quantity at each node is simply given by the application of the Laplacian on top of the state of the network itself. And you can see these in the propagator form that takes simply the exponential form given the initial condition. And this has been used in the past years for probing network structures, because as you can see, it has this ability to reveal like scale linking to the spatial scale, let's say, that are intrinsic, that a network and heterogeneous networks in general lacks, by linking the temporal scale of the evolution of the process to the spatial scale, that is the state of the process at some time. And now we come to the part about the results of how can we probe disorder and frustration, while quench disorder, as I mentioned, has already been tackled in the past years in the network realm. And can we do something similar when we add this sort of frustration cycle into our system? And it comes to our help the presence of in literature of this signed Laplacian operator, which is, we can see it in the continuum as the same Laplacian of the underlying topological substratum, plus a term which is unspecified, but it can be represented, that encodes the location of what we will call defects. They are really negative links into the discrete topology. And the writing of the operator is the very same, but you take the absolute value of the entries of your coupling matrix so that you have a positive definite operator. And to test what kind of diffusion is this operator encoding, we just simulated it on a simple lattice with a negative link. And what happened is that as soon as you add the negative link, which creates many loops of frustration because there are negative, oddly product of negative links cycles at any order, what you obtain is that if you measure the field at equilibrium, you see that there is this sort of sink effect, logarithmic sink effect. That is, it acts locally as a sink sucking the information from the system, while globally has a little effect. So now let's say that we put a fraction p of negative edges into the system, and we look into the spectrum of this operator. And what happens is that we have a sort of tantamount process to the Anderson localization in the spectrum. That is, the lowest eigenmode become localized. The measure localizes into a subset of the system. And if you analyze over order of magnitude, you see that a non-trivial structure is emerging in the spectrum. And if you further take the sign, you see this sort of fractal images when you have enough negative links. So we have these two sides phenomenology of localization and a sign structure emergence. Turns out that if you pick a graph and assign -1 weights with to a fraction of p of the edges, and then you take the sign of the lowest eigenvector and you reproject it on the topology itself, you can define an order parameter that is actually describing a percolation transition. And in particularly, you can see, like here in 2D square lattice and in a 3D lattice, that when you have P way lower than the critical threshold, you have some sort of homogeneous state, whereas if you go on by adding negative links, the frustrated loops makes this fractal structure emerges that we figured out that it was actual percolation, as I'm going to show you in a moment. And I would like to show you the difference of how you pass from the unfrustrated case to the frustrated one. So you have the usual plane waves mode, and then they all fragments, and there is a sort of collapse in the eigenvalues of your operator. This process, as I told you, as I anticipated, is a percolation transition, and actually is an isotropic percolation transition, as we spotted from the Fisher exponents over different topologies, and it can be mirrored in the real space by adding like percolation of the disk, like there is the influence radius that define this transition at the critical value where the eigenmode fragments. You also observe the percolation of this disk through the system. And the nice thing about this framework is that it's totally generalizable because it's based on the Laplacian, discrete Laplacian, which is you can adapt it to any kind of topology you want. And we tested many topologies, and we found more or less the same phenomenology, that is a peak and sometimes two peaks. There is a non-trivial structure also in this, especially when you start looking at the fluctuation of the critical parameter. But for now, the most interesting part is that if you compute all of these critical parameters, then it turns out that those passionate about spin glasses will recognize this as the critical parameters of the so-called random bond Ising model, that is really the Edward Anderson Hamiltonian that we saw in the beginning, at 0 temperature in the phase diagram T and P. And it's the onset of the spin glass phases at 0 temperature. And so the Edward Anderson Hamiltonian, when you take plus and minus J, has the transition marked by a purely structural feature. And in particular, if you carry out a bit of mathematics and look at the field theoretical description from the partition function, turns out that the discrete field is really completely equivalent to the equation of the eigenmodes of the sign Laplacian, up to the fact that in one case you're treating a discrete field, so you're optimizing over a hyperdimensional cube. In the other case, you're optimizing over the hyperdimensional sphere, so it's the continuous equivalent. And this also explains how the transition emerges in this kind of system. And if you start measuring the energy of these eigenmodes on top of the system, where you plug them into your Hamiltonian, you find that below the critical fraction threshold, the order of the states of the Laplacian is the very same of the order of the energy minima, and it's you can represent it like this, like energy levels, and they are ordered exactly with the eigenvalues of the Laplacian. And the lowest eigenmode is always the lowest mode, the lowest state of energy state of the system. While when you overcome the critical threshold, it turns out that all of these modes, like the lower modes, start collapsing because they want to invert the order, because when you would have flipped all of your links, you would have arrived at the completely antiferromagnetic, so the highest mode becomes the lowest energy, and so on. But in this in-between situation, it turns out that there is this sort of degeneracy. They become comparable all in energy, still sitting at the lowest energy of your system. And so this inversion is like the degeneracy that kind of explains structurally the spin glass transition. Now, all of this framework can be played around, like starting to probe different kind of correlated disorder and stuff that is really interesting nowadays, especially with AI posing problems and understanding what's going on inside the black box at the dynamical level. And for example, we started flipping crosses instead of single links. We flip all the links for each node. And it turns out that in this case, you have two transitions. One is the clear mark of the onset of non-ergodicity. So all the lowest mode become, when you quench your system, become some stable local minima that fluctuates around this minima, while at the other critical point, it turns out that the real spin glass phases emerges. And in this case, we call it this system like an hope-filled memory, like you can encode in this system memories as a superposition of this lowest mode. And it turns out that the minima are well separated until you overcome this 0.4 second threshold, which is the mark, is the onset of the competing transition, where regions start competing, and so you have clearly separated the two phenomena, so non-ergodic phase and glassy phase, also at the structural level. That was impossible to see with the single links because of the chaotic nature of the other kind of disorder. To make this very general and not dependent on ferromagnetic Hamiltonians, we kind of introduced a new excitation inhibition inspired model, let's say, where your system can be active or inactive, like 0, 1, and the probability, there is no Hamiltonian here, no energy landscape, is totally out of equilibrium system, and the dynamics is like two-state bistable dynamics, when you have no negative links, where the process either die, either survives, depending on the parameter gamma. While when you start adding negative links, it turns out that these low decaying processes start emerging, and at the critical point exactly in one point in gamma, while above the critical point an entire phase dominated by Griffith phase and the onset of competition between mesoscopic region start dominating the system. And so we kind of proved that is much of the structure that explain also the emerging of some important dynamical transition in this kind of antagonistic dynamical system. Some few key implication from we can start with the basic one, that is we can define like local order measures of the system, which are based on these on the structure of the system itself. So that, as you can see, for example, if you want to reconstruct the phase diagram of a spin glass, you start simulating your spin at time t, and then you can reproject it on top of the lowest mode. In the case of the single links, where you have only non-ergodicity and the onset of spin glass competition matching, you will need only the lowest one. But when the two things are split, like in the case of the X cases or in the X of different dynamics, you might need to study these on top of the lower M modes of the dynamics. Or otherwise, you can proceed by looking at the structural percolation clusters that the eigenmodes define themselves, and define the sort of local magnetization of the giant cluster, and measure the order as a local order on top of this. And again, it can be repeated on top of higher modes more and more as more the information it's required to describe your dynamics. A third parameter, which is order parameter, which is interesting and is basically very same to this one, is the so-called reconstructability. So the exercise now is you take the state of your system and then you try to reconstruct with the first m modes of your sine Laplacian. So for example, in this phase diagram, this is the Edward Anderson plus minus j in 3 dimension. You see that if in the ferromagnetic phase with 8 mode, you describe the whole picture. In the paramagnetic phase, you don't describe anything, while in the spin glass phase, you have this in-between situation in which structural feature really determines quite a lot of your system. And this is totally general and it's gathering competitive interaction from geometric frustration that is spin ice with spin glasses and everything else. Because, for example, you can now simulate the completely frustrated antiferromagnetic triangular and then try to reconstruct it. The same exercise. What happens is that your reconstruction allows you to draw the phase diagram of the antiferromagnetic between a phase where the slow dynamics of geometric frustration dominates and the phase where the paramagnetic effects dominates on the other side. Some key implication from the glassy transition on is that these are mostly conjecture, except for the fourth one, like, for example, the problem on the upper critical dimension of the spin glass is like, you can think of it as if the topological substratum in which the actual Ising, the effective Ising is moving is a fractal percolating cluster, then the effective dimension will be you need to have for the mean field to hold, you need to be in the percolative mean field range, so it's dimension 6, where the dimension of the fractal dimension of your percolating cluster is 4, which is exactly the Ising upper critical dimension. And so this is a possible geometric explanation of the reason of the upper critical dimension. Then we have the explanation of reentrances in phase diagrams as the breaking of the small percolating clusters at higher temperatures that make the system more robust. And another conjecture is that actually the algebraic signature of non-trivial structure emerges in the energy landscape as the ultrametric structure of minima can be described and better embedded with within the space of lower eigenstates of the system. And to finally show some interesting consequences that now if you take, for example, you can observe the replica, let's say, symmetry breaking on top of this stochastic differential equation, where you simply take the sin Laplacian, you add a very small noise to the system, just because otherwise it's simply deterministic. And what happens is that exactly at the critical fraction of negative links, the system start, if you simulate the system over and over, is start creating a non-trivial overlap structure in the very same spirit of replica symmetry baking. This is like the end, some few perspective and application that are really just the beginning, because it was much of a theoretical construction and understanding. But now that we have kind of a picture of the whole, we are trying to start seeing which kind of application can we do. And one very clear is like trying to apply this for, we can build this kind of topological autoencoder, which cost zero training because they are just the linear projection of your data on top of your structure. It turns out very straightforwardly that if you use different topologies, you get very better reconstruction. So, for example, for 2D images, the reconstruction that you obtain with a few modes of 2D lattice is almost perfect. With a triangular all frustrated is terrible. And the same have been seen, like with the regular Laplacian, for example, in the brain networks, where they already noticed that this kind of reconstruction by using the topological substratum, in that case of the brain itself, is the best, like, let's say, embedding space. And really the final results, that all of this, it can be found in the 2 archives that are still since long under review, and is a topological inspired spectral optimizer, which is based on the cross entropy method. But now you move the problem of finding the minimum configuration on top of the optimizing of your of the coefficient of the first M modes. So for example, you see that with M modes, you obtain a certain energy. With more modes and so on, you start scaling towards the simulated annealing benchmark. So with a purely topological shuffle of your coefficients in your Laplacian expansion, you are getting like the minimum. You are like moving the dynamical problem to a sort of algebraic combinatorial realm, which might be interesting and worth investigating more. So we have the take-home message is that we have started this process of disentangling topology and dynamics inspired from network theory, and with the fashion and with the interest in the disordered system, and in general for antagonistic interaction, where we discovered that much of the structure contain really a lot of information about the systems, and so it might be worth investigating more. Thank you for your attention.
Thank you, Giulio. Are there any questions? Apparently not. Maybe I have a curiosity because, but I don't know if I understood correctly, because there were a lot of information in your talk. But so from your approach, is it possible to learn something about the dynamics of the spins? Because you show that you can learn about equilibrium properties or static, but suppose you drive your system out of equilibrium. Can you say something?
Yes, I think the answer lies more or less in this kind of order parameters, like as you see, like there's some sort of time dependent in the sense that it's not like we haven't yet studied like the non-equilibrium properties of the system itself, but it's definitely interesting to see what's the behavior of these, for example, topology-inspired order parameters when you start perturbing or setting up the system into non-out of equilibrium states. But we haven't yet, let's say, started that. There is a lot of direction going on. So we started with a picture of reconstructing the equilibrium properties that we know from literature and extending these to like more complicated topologies. But definitely this is a terribly interesting direction to go, because of course I think much part of what is not understood yet in this kind of system is that. So I think this is a good framework for doing that, in the sense that our idea for out of equilibrium study is that first we have to understand what's the best embedding, let's say, how do we embed the dynamics, in these lower modes. Once you know that, I think you can kind of embed also these order parameters out of equilibrium, or I don't know, maybe do some fluctuation dissipation. I'm not really sure on how to do this, but it's definitely a very interesting research direction.
Okay, thank you. Any other question? Okay. So if there are no other questions, we can thank the speakers again.
Thank you.